if you ask a theoretical physicist to define the concept of time, you're going to get an entirely completely different answer depending on which room in the university you happen to be standing in.
Oh, absolutely. It's a mess.
Right. Because if you're in the classical mechanics lab, time is just this, ticking clock on the wall. But if you walk over to the cosmology department, time is a physical dimension. It's woven into the fabric of reality itself. It's bending and stretching.
Yeah, then you walk across the hall to the quantum mechanics department.
And suddenly time goes right back to being a rigid, unmoving background stage.
Exactly.
And if you dare to step into the thermodynamics department, time is simply a measure of decay. It's just a statistical likelihood that things are getting messier.
The arrow of entropy.
Yes. So for over a century, modern physics has basically been hiding this massive fundamental secret in plain sight. Our core definitions of reality are entirely contradictory. We are looking at the universe through a completely broken lens.
Yeah, and the scientific community, well, they rarely refer to it quite so bluntly in public, but behind closed doors, it is universally acknowledged. We call it the crisis of time.
The crisis of time.
Right. It is the unspoken elephant in the room of modern physics. And honestly, it is the primary reason why we have fundamentally failed to unite the macro world of gravity with the micro world of quantum mechanics.
Which brings us to the absolutely staggering stack of sources we are diving into today.
Yeah.
And when I say staggering to you listening right now, I mean a literal desk-breaking pile of physics treatises.
It's heavy reading, literally and figuratively.
For sure. We are looking at volumes A through D of a framework called the TFH Principia. We've got these incredibly dense, math-heavy papers with, honestly, incredibly bold titles. Titles like Replacing GR.
Meaning general relativity.
Right, and Replacing QFT, which stands for Quantum Field Theory. So the mission for our deep dive today is to really unpack this radically ambitious, comprehensive proposal called the Time Force Hypothesis, or TFH.
And it is arguably one of the most sweeping attempts to rewrite the bedrock of physics that we have seen in, well, decades.
Yeah.
What makes these sources so fascinating isn't just the math. I mean, the math is extensive, obviously, but it is the underlying philosophy. TFH is proposing to throw away almost everything we think we know about the building blocks of the universe and start over from a single unified axiom.
And we are going to explore exactly what that axiom is, how it aims to rewrite the textbooks, and I think most importantly, what it would actually take for the deeply entrenched mainstream scientific community to accept something this radical.
Because that's the real hurdle, isn't it?
Oh, totally. Because as you'll see as we go through this with you, TFH is a very unique, almost wholesome X factor in how it presents itself to the world of science. But to understand the cure being proposed here, we really need to dig deep into the disease first.
The broken lens.
Exactly. You mentioned the crisis of time. Let's break down exactly why our current models are so fractured. Starting with classical mechanics. This is Isaac Newton's world, right?
That is a perfect place to start. So if you open a standard high school physics textbook on classical mechanics, you see time treated as an absolute external parameter.
Right.
It is Isaac Newton's universal, invisible, ticking clock. In Newton's equations, time is completely independent of the physical events happening within the universe. It sits outside of reality, dictating the pace of events, but it's never actually affected by them.
So whether two massive planets are colliding or feathers just falling in a vacuum, Newton's clock just marches forward at the exact same unyielding speed,
Exactly.
which feels very intuitive, like it matches our everyday human experience.
It feels intuitive until you start moving very, very fast or get very heavy. That is where Albert Einstein enters the picture and completely shatters Newton's absolute clock.
Right, the game changer.
In general relativity, which is Einstein's masterpiece, time is no longer a background parameter sitting outside the universe. It becomes a coordinate intrinsically woven together with the three dimensions of space into a four-dimensional fabric we call space-time.
And this is the famous rubber sheet analogy, right, where massive objects like the sun warp the fabric around them. But it's not just space that warps. It's time, too.
Yes, and that warping of time is a measurable fact. It's not just theory. A clock sitting on the surface of the Earth, deep in our gravity well, literally ticks slower than a clock on a GPS satellite up in orbit.
Which is still wild to think about.
It is. Time is relative to your speed and your proximity to mass. But the philosophical consequence of Einstein's math is even more unsettling. It leads to the concept of the block universe.
Oh, man. The block universe.
Because time is just a coordinate, right? Like up, down, left, or right. Einstein's equation suggests that the past, the present, and the future all coexist as a single static four-dimensional structure.
And that concept has always just melted my brain a little bit. The idea that there is no objective flowing now. That, the Roman Empire, your morning cup of coffee, and the death of the sun are all just different coordinates sitting there permanently in this frozen block of space-time.
It implies a profound determinism that many physicists, frankly, find deeply uncomfortable. But the crisis doesn't stop there.
Of course not.
The real breaking point happens when you leave Einstein's macroscopic world of stars and galaxies, and you attempt to analyze the microscopic world of atoms and subatomic particles. You transition to quantum field theory, or QFT.
And QFT is arguably the most successful, precisely tested theory in human history, right? I mean, we use its mathematics to design the microchips in the phone you're probably listening to this on, and the lasers in fiber optic cables. It works.
Oh, it works beautifully.
But how does it treat time?
It reverts right back to Newton.
Wait, really?
Yes. Despite Einstein proving that time is dynamic and woven into space, quantum field theory treats time as a fixed, flat, external background parameter.
Wow.
QFT requires a rigid stage on which quantum events can unfold. It calculates the probabilities of particles interacting over time, but the time parameter itself doesn't dynamically interact with the particles.
So Einstein is saying the stage itself is warping and bending, but quantum mechanics is over there saying, no, we can only do our math if the stage is perfectly flat and rigid.
You have hit on the exact mathematical contradiction that has stalled physics for a century. When you try to combine these theories...
Make a theory of quantum gravity.
Exactly. When you try to formulate quantum gravity to understand what happens at the center of a black hole or at the exact moment of the Big Bang, the math produces infinities. It breaks down completely because you are trying to plug a dynamic warping coordinate into an equation that explicitly demands a flat, unchanging background.
It's like trying to run Mac software on a Windows 95 machine.
It just crashes.
It fundamentally crashes.
And just to add one more layer to this massive headache, we have the thermodynamics department. And they don't care about background stages or warping fabrics. They care about heat and entropy.
Right.
To them, time is just the arrow of entropy. It's the statistical observation that a dropped coffee mug shatters, but shattered porcelain never spontaneously reassembles into a mug. Thermodynamics provides the arrow, the directionality of time, but it doesn't explain what time fundamentally is. So as you outlined at the start, we have Newton's absolute clock, Einstein's frozen block universe, QFT's rigid stage, and thermodynamics' arrow of decay.
It's a mess.
They all use the letter T in their equations, but T means something entirely different in every single framework.
Okay, so I think we firmly established the disease here. Physics is suffering from a massive identity crisis regarding the fundamental nature of reality, and this is where the time-force hypothesis steps in with a pivot so foundational, it kind of forces you to rethink everything you thought you knew about the universe.
It does.
I want to read Axiom 1 of the TFH Principia directly from the source text because it is just breathtakingly bold. Axiom 1, energy exists and nothing else does.
It is a radical ontological simplification.
Ontology being the philosophical study of what actually exists, right?
Right. The authors of TFH are attempting to clear the board entirely.
But I'm struggling to see how we just throw away space-time. How do we throw away the 17 fundamental particles of the Standard Model, the 4 fundamental forces, and just declare only energy exists? Well, if only energy exists, what is the universe? Where is the energy sitting?
Well, to grasp this, we have to strip away our preconceptions of a spatial vacuum containing objects. TFH proposes an energy-only ontology by mathematically representing this fundamental energy as a single scalar field.
Okay.
They denote it using the Greek letter phi. Now, this field is defined as existing within a four-dimensional Euclidean bulk.
Okay, let me stop you right there. Because to anyone who isn't a theoretical physicist, four-dimensional Euclidean bulk sounds incredibly intimidating. We need to unpack that for the listener.
Sure. So a Euclidean space is essentially the flat, standard geometry you learned in high school, just extended.
Like graph paper.
Exactly. A piece of paper is a two-dimensional Euclidean space. The room you are sitting in is a three-dimensional Euclidean space. A four-dimensional Euclidean bulk simply adds a fourth spatial direction. But crucially, we must differentiate this from Einstein's four-dimensional spacetime. In Einstein's model, you have 3 dimensions of space and 1 dimension of time. In TFH, the bulk is 4 dimensions of pure space.
Wait, pure space?
Yes. Time is not a coordinate in this bulk. Time does not exist as an axis you can point to.
So the bulk is just this vast, infinite, four-dimensional ocean of static energy. There is no time. There is just this spatial ocean. How does anything happen then?
Imagine a localized excitation within that four-dimensional ocean, a disturbance.
Okay.
This disturbance generates a wave of energy that begins to expand outward radially. TFH proposes that the observable universe, everything you, I, every telescope, and every particle accelerator has ever interacted with, is not the four-dimensional ocean itself.
It's not the ocean.
No, it is merely the three-dimensional moving boundary of this expanding wave. The authors term it the wave face, or the wavefront.
I want to make sure I'm visualizing this correctly, because this seems like the core of the entire theory. Let's use an analogy. Think of a perfectly still pond. That's a two-dimensional surface. You drop a stone into it. That's the initial disturbance.
Right.
The stone creates a one-dimensional ripple, like a circular line of raised water that expands outward.
That is a highly effective analogy, yes.
So in TFH, the pond is the 4D Euclidean bulk.
Yeah.
The splash is whatever initiated the universe. And the universe that we actually experience, the stars, the planets, our bodies, is just the physical ripple moving outward. We are living entirely on the leading edge of the wave.
That captures the geometry perfectly. You and I and the entire observable cosmos are confined to the three-dimensional surface of that propagating wave face.
Which means the present moment, our concept of now, is literally just the physical edge of that ripple.
Yes.
The interior of the ripple, the space the wave has already passed through, is the past. The physical path is just the history encoded in the field behind us. And the untouched water ahead of the ripple.
The untouched bulk ahead of the wave face is a future that physically has not come into existence yet. It simply hasn't been disturbed. And this brings us to the most profound paradigm shift in the entire TFH framework. We finally have a unified definition of time.
What is it?
Physical time is explicitly defined as the advance of this wavefront.
The universe doesn't evolve in time. The universe is the evolving front.
Precisely. What we experience biologically and physically as the relentless flow of time is simply the radial progression of this scalar wave moving through the 4D bulk. Time is not a dimension. It is a mechanism of motion.
That is wild, because if you've ever looked at a textbook on string theory or supersymmetry, you know that mainstream attempts to solve the crisis in physics usually involve adding layers of complexity. Right, like the math for quantum gravity isn't working. Let's add 6 more hidden, curled-up spatial dimensions. Let's add an entire mirror universe of supersymmetric particles that we just can't see. They patch the leaks by adding more plumbing. But TFH's ultimate X factor is its profound economy. It does the exact opposite. It strips reality down to a single substrate.
String theory and similar unification frameworks really suffer from a massive proliferation of free parameters and unobservable dimensions, which makes them notoriously difficult to test or falsify. The elegance of TFH lies in its reductionism. It posits one field, one wave.
This one.
And from the dynamics of this single propagating field, the authors attempt to derive the geometry of space, the rules of quantum mechanics, the masses of particles, the force of gravity, and the evolution of the cosmos.
And it completely reframes the thermodynamics problem too, right? The arrow of time. Because in standard physics, the fact that a dropped coffee mug shatters but never reassembles is often treated as just a statistical accident of the Big Bang. The universe just happened to start in a highly ordered, low-entropy state, and it's been getting messier ever since. But in TFH, the arrow of time isn't an accident of initial conditions.
No, the arrow of time becomes an intrinsic mechanical necessity of the field itself. As the 3D wavefront propagates outward through the 4D bulk, the scalar field undergoes a process the authors call irreversible equilibration.
Irreversible equilibration. Let's break that down.
Okay, imagine any wave traveling through a medium. As it expands, it is dynamically damping. It is losing its sharp peaks, losing amplitude, and redistributing its concentrated energy across a wider and wider surface area.
Yeah, it flattens out.
Exactly. The arrow of time is the literal physical direction of the wavefront's dissipative propagation. You cannot unring a bell, and you cannot force an expanding, damping wave to suddenly concentrate its energy and shrink backward. The macro world gets messier because the wave is continuously spreading and flattening.
But hold on, I have a major point of confusion here, and I think anyone picturing this wave would hit the same exact roadblock.
Let's hear it.
If we are literally just a ripple of energy moving through a 4D ocean, and that ripple is constantly spreading out and losing its sharp peaks, what happens when the ripple runs out of steam? Doesn't a wave eventually dissipate so much that it just fades away into perfectly flat water?
Anticipating that exact objection is where the architects of TFH transition from philosophical concepts into rigorous mathematics. You are identifying the core mechanical driver of the entire theory here. The wave does indeed run out of steam, but that fading process is not a flaw in the model. It is the engine that drives the evolution of the cosmos. This dissipative process is explicitly governed by the central mathematical pillar of the theory, which is the TFH master equation.
Let's get into the master equation then, because the sources dedicate an enormous amount of space to it. It is described as a damped, nonlinear wave equation. And there is one specific mathematical term in this equation that seems to carry, like, the entire weight of the universe on its shoulders. It's the universal damping rate, which they denote as alpha zero.
Alpha zero is unarguably the most crucial parameter in the TFH framework. It represents the specific mathematical rate at which the scalar wave loses amplitude, or runs out of steam, as you put it, as it propagates radially through the bulk.
Okay.
The authors propose that the universe has been propagating for a very long time and has entered a late-time equilibrium state. In this current state, they mathematically identify this fundamental damping scale, alpha zero, with a very famous number in astrophysics, the Hubble constant.
The Hubble constant. We really need to expand on why that connection is so wild. The Hubble constant, generally denoted as h0, is the number that tells us how fast the universe is expanding.
Correct. When astronomers look out at distant galaxies, they observe a phenomenon called redshift. The light from these galaxies is stretched out toward the red end of the spectrum.
Because they're moving away from us.
Right. The further away a galaxy is, the more its light is stretched, which indicates it is moving away from us faster. The standard cosmological interpretation of this observation is that the metric of space itself is expanding, like a balloon inflating, carrying the galaxies along with it.
But we established earlier that in TFH, there is no fundamental metric of space. Space is not a fabric. Space is just the induced geometry, the surface appearance of the moving wavefront. So if there's no spatial fabric to inflate, how does a damping wave cause the observable expansion of the universe?
Okay, visualize the wavefront as a highly tensioned, vibrating membrane.
A membrane, got it.
The localized vibrations on this membrane are the concentrations of energy we perceive as matter. Stars, planets, galaxies. As the whole wave face propagates forward through the bulk, it is subjected to the universal damping rate, alpha zero. Its vertical amplitude, its physical intensity decays. But the fundamental physical action of the system must be conserved.
And action conservation is a core tenet of physics. You can't just delete energy and momentum. It has to balance out somewhere.
Exactly the point. Because the vertical amplitude is dropping, the geometry of the wave must compensate. The horizontal wavelengths of all the excitations confined to the front must effectively stretch to conserve the action.
So as the wave loses its vertical height, it essentially gets pulled apart horizontally to make up the difference.
That is the mechanical consequence, yes. Now imagine you are an observer made of this vibrating energy, living entirely on the surface of this membrane. Your telescopes, your rulers, your very atoms are part of this stretching geometry. To you, the observer trapped on the wave face, this universal stretching of wavelengths is completely indistinguishable from the space between distant objects physically expanding.
That is an incredibly elegant synthesis. I mean, TFH is proposing that the microscopic and the macroscopic are driven by the exact same mechanism. The damping rate that causes a coffee mug to shatter and drives the arrow of time forward is the exact same mathematical mechanism that causes the observable expansion of the universe. The universe isn't inflating. The wave we live on is just fatiguing and stretching out.
It connects the evolution of time directly to the evolution of space in a way that standard models completely miss. And in doing so, TFH profoundly reframes what is arguably the most embarrassing mathematical failure in modern theoretical physics.
Oh, I know where you're going with this.
The vacuum catastrophe of quantum field theory.
The vacuum catastrophe. This is a piece of physics history we absolutely need to dive into for you guys listening because it shows just how badly the current models are struggling. Walk us through what the vacuum catastrophe actually is.
Well, in quantum field theory, the vacuum of empty space is not truly empty. It is a roiling, boiling sea of virtual particles constantly popping in and out of existence. According to the rules of QFT, every fundamental field has a baseline energy level, a 0-point energy.
Right.
If you try to calculate the total energy density of the vacuum by adding up the 0-point energies of all these quantum fields, the math gives you an impossibly massive number.
How massive are we talking?
The theoretical calculation of the vacuum energy is roughly 120 orders of magnitude larger than the actual observed energy density of the universe.
Wait, a 120 orders of magnitude?
Yes. To put that in perspective, 120 orders of magnitude isn't just a rounding error. It is considered the single worst prediction in the entire history of theoretical physics.
It's a number so wrong it almost defies comprehension. Like, there aren't even analogies for being that wrong.
And the problem becomes catastrophic when you combine that calculation with general relativity. In Einstein's equations, any form of energy density, including vacuum energy, acts as a source of gravity. It curves space-time.
Okay, so if the vacuum has that much energy,
If QFT is right about the immense energy of the vacuum, the gravitational pull of empty space should be so strong that the entire universe would have curled up into a microscopic ball the size of a proton a fraction of a second after the Big Bang.
but obviously we are here. The universe is massive and expanding. So how does mainstream cosmology fix this glaring contradiction today?
They apply a mathematical patch. Cosmologists introduce a term called the cosmological constant, denoted by lambda. This represents a mysterious, invisible substance we call dark energy. Dark energy is theorized to be a repulsive force inherent to space itself, pushing the universe apart. To make the universe look the way it does, physicists have to finely tune the value of dark energy to an absurd, almost comical degree, just to perfectly cancel out the massive vacuum energy predicted by QFT.
It's the ultimate cosmological duct tape. You invent an invisible fluid that pushes everything apart just to counter the invisible math that says everything should crush together.
Pretty much.
How does TFH sidestep this whole mess?
TFH avoids the vacuum catastrophe by severing the link between vacuum energy and geometric curvature. Because TFH does not use Einstein's fundamental spacetime metric, the underlying energy of the scalar field doesn't automatically act as a gravitational anchor trying to crush the universe.
So the background energy of the wave is just the background energy. It doesn't instantly dictate the curvature of a space-time fabric because the space-time fabric doesn't exist in the first place.
The cosmological consequence is profound. In TFH, dark energy is not a new, mysterious, repulsive substance that we need to spend billions of dollars trying to capture in a detector. Dark energy is simply the macroscopic, observable effect of the background scalar field undergoing its natural damping process.
The universe's accelerated expansion isn't being pushed by a ghost fluid, it's just the natural fatigue of the 4D wave.
Yeah.
I have to ask, though, does the math actually hold up? Because anyone can say, oh, it's just a fading wave. But cosmologists have incredibly precise measurements of how dark energy actually behaves out there.
The math is highly rigorous. Cosmologists characterize dark energy using an equation of state, a parameter they call W. In standard lambda-CDM cosmology, for the dark energy model to work, the value of W must be exactly -1, a perfect, unchanging constant.
Okay.
However, the TFH master equation, driven by the damping parameter alpha 0, naturally predicts that an expanding damping wave will yield an effective equation of state where W is approximately -1.
So it naturally yields the accelerated expansion without needing to invent a new substance to balance the books.
The elimination of dark mysteries is one of the most compelling aspects of the TFH framework. It strips away the ad hoc patches. But proposing that space isn't expanding and that dark energy isn't real forces TFH into a very difficult corner.
Because of gravity.
Right. If you throw away Einstein's metric of curved spacetime, you still have to explain gravity. You still have to explain why the Earth orbits the sun and why an apple falls from a tree.
Which brings us to a massive, crucial part of the TFH Principia. They have to replace general relativity. Einstein said that matter tells space-time how to curve, and curvature tells matter how to move. The classic rubber sheet analogy we mentioned, right? You put a heavy bowling ball on a trampoline, it creates a deep dip in the fabric, and a smaller marble rolling past will get caught in that dip and spiral inward. It is a beautiful, intuitive model. If TFH is throwing the trampoline in the garbage, what replaces it?
The authors introduce a framework they call topography, which is mathematically denoted as T of x.
Topography. Like reading the elevation lines on a map of a mountain range.
The analogy holds. While there is no fundamental rubber sheet, there is the moving, three-dimensional wavefront of the scalar field. Topography is the TFH language for describing how the underlying dynamics of the scalar field cause certain localized regions of the wavefront to become energetically deep or shallow.
How does energy create depth without curving a fabric, though?
When the scalar field's energy is highly concentrated in a specific configuration, like a dense knot of vibrations that we perceive macroscopically as the sun, for example,
Right.
that concentration fundamentally alters the propagation dynamics in that local area. It thickens the wavefront. It carves ruts, valleys, and pressure gradients into the geometry of the propagating wave.
So gravity is completely redefined. It is no longer the curvature of a permanent background spacetime fabric. Gravity is the trajectory deviation induced by the thickness and the ruts in the advancing wavefront.
It is an emergent phenomenon, and the most striking mathematical proof of this is how TFH handles Newton's gravitational constant, g.
Oh yeah, let's talk about G.
In both Newton's laws and Einstein's equations of general relativity, g is a fundamental constant of nature. It's a number, about 6.67 times 10 to the negative 11, that you simply have to plug into the equations by hand to dictate the ultimate strength of gravity. Standard physics has absolutely no explanation for why g has that specific value.
It's just a dial that was set at the factory.
In TFH, g is not a fundamental, arbitrarily chosen input. It is an emergent response coefficient. It is a derived value that quantifies exactly how the geometry of the wavefront responds to the presence of scalar field energy. Gravity isn't a fundamental force programmed into the universe. It is the unavoidable geometric consequence of energy moving through a wave.
The sources use an analogy for this that I found incredibly helpful because honestly, visualizing a 4D wave is tough. They draw heavily on geophysical fluid dynamics. They compare the universe to planetary weather.
It's a robust comparison that maps well to the mathematics of the TFH topography.
Think of our universe not as an empty static stage where objects float around, but as a violent atmospheric weather front. A sharp, dynamic, three-dimensional structure moving relentlessly through a four-dimensional ocean of air.
Yes.
In a weather system, you have high-pressure zones and low-pressure zones. When the wind blows, it isn't being pulled by a magical fundamental wind force acting at a distance. The air moves simply because it is following the pressure gradients. It is flowing down the topography of the atmosphere.
That is an excellent visualization of trajectory deviation. In TFH, localized patterns of concentrated energy, the stable structures we call planets, stars, or galaxies, are essentially caught in the weather patterns of the scalar field. They are moving along the pressure gradients, the geometric ruts carved into the wavefront.
Okay, conceptually, I love the weatherfront model. It's incredibly elegant, but physics is a brutal, numbers-driven discipline. It doesn't matter how beautiful your metaphor is if it doesn't match the data. Einstein's general relativity has survived over a century of the most rigorous testing imaginable. Does this TFH weatherfront model actually hold up against the classic tests of GR?
Any new theoretical framework must reproduce the established, verified successes of the theory it intends to replace. The authors dedicate almost the entirety of Volume C to proving that TFH topography passes these gauntlets. They meticulously demonstrate that the math of the wavefront recovers the anomalous perihelion precession of Mercury.
Let's remind people what that is, because it was the first great triumph of Einstein's theory.
Mercury's orbit around the sun isn't a perfect closed ellipse. It slowly traces out a rosette shape over time. Newtonian gravity could account for most of this shifting, but there was a tiny residual wobble that Newton's equations simply could not explain. General relativity showed that the extreme curvature of space-time near the massive sun perfectly accounted for the missing wobble. TFH shows that the dense topographic rut created by the sun on the wavefront yields the exact same trajectory deviation for Mercury.
And it doesn't stop there. They also tackle the Shapiro time delay.
The Shapiro delay is the phenomenon where a light signal slows down as it passes through a strong gravitational field. General relativity explains this as light having to travel a longer distance through the curved dip in spacetime. TFH explains it as the light wave physically slowing its propagation speed as it moves through the energetically dense, thickened topography of the wavefront.
They also mathematically recover the bending of starlight around galaxies, known as gravitational lensing and gravitational redshift. So in our local solar system, the topography model mimics Einstein's rubber sheet perfectly. But the real test of gravity theory today isn't in the solar system, it's out in the deep cosmos. What happens when TFH looks at a whole galaxy? Because that is where Einstein's equations start to fail without the invention of dark matter.
The dark matter problem is the second massive crisis in modern cosmology, right alongside dark energy. When astronomers measure the rotation speed of spiral galaxies, they find a glaring anomaly. Based on the amount of visible matter, the stars and the gas we can actually see, the outer edges of these galaxies are spinning far too fast.
Way too fast.
According to standard gravity, there isn't enough mass to hold them together. They should be violently tearing themselves apart and flinging stars into the void.
But they don't fly apart. So standard cosmology solves this by assuming that every galaxy is embedded in a massive, invisible halo of dark matter. It's theorized to be a new, weakly interacting particle that doesn't emit or reflect light, but exerts a massive gravitational pull.
We've been searching for this particle for decades using massive underground detectors, and we have found absolutely nothing. TFH looks at this galactic rotation problem and proposes a radical alternative. There are no missing invisible particles.
So what holds the galaxy together?
In TFH, what standard cosmology calls dark matter is simply a phenomenon of enhanced warping in the wavefront's topography.
Enhanced warping. You need to explain how the wave warps more than the visible matter allows.
You have to remember that the topography T of X is history-dependent. The wavefront is not a memoryless system. As the universe propagates and massive structures like galaxies evolve, merge, and swirl over billions of years, they leave incredibly deep, complex, and persistent ruts in the scalar field.
Oh, I see.
The dynamic configuration of the scalar field can produce stronger, effective curvature, deeper valleys, than the current distribution of visible matter alone would suggest.
I want to make sure I grasp this. It's almost like a phantom rut. The visible stars we see today are sitting in a topographic valley that was carved out and deepened by the complex, turbulent history of the energy wave itself, not by a cloud of invisible ghost particles sitting there right now.
That is an apt description. The gravity is real, the rut is real, but the source of the rut is the dynamic history of the field, not an invisible form of matter. The authors even provide a comprehensive TFH translation dictionary. Whenever general relativity relies on its stress-energy tensor to map the distribution of matter to curvature, TFH mathematically maps that exact same effect to an effective tensor derived purely from field dynamics and historical topography.
Here is my biggest issue with everything we've discussed so far, though. If TFH perfectly mimics Einstein's math in the solar system and perfectly mimics dark matter through these phantom ruts in the galaxies, how would we ever know who is right? If the output looks exactly the same, it's just a philosophical debate, it's metaphysics. What is the smoking gun that proves we are surfing on a 4D energy wave and not sinking into a 4D Einsteinian rubber sheet?
You are raising the most critical point of the entire framework. If TFH merely acted as a perfect mathematical shadow of established theories, physicists would dismiss it as an overly complex mathematical curiosity. To find the smoking gun, to find the measurable divergence, we must leave the macroscopic world of gravity and telescopes. We have to transition into the microscopic world of the quantum and atomic scales.
The tiny stuff.
This is where TFH ceases to mimic the established models and makes stark, highly falsifiable predictions.
Let's dive deep into the quantum realm, because this is where the theory takes its biggest swings. We're talking about replacing quantum field theory, deriving the entire standard model of particle physics from scratch, and hunting for the ultimate prize, the 2.05 GeV mass gap.
To appreciate the magnitude of what TFH is attempting here, we need to understand how standard quantum field theory operates. QFT is the engine behind the standard model, which successfully categorizes all the known fundamental particles. The quarks that make up protons, the electrons, the photons of light, the Higgs boson.
And, as we said earlier, it is terrifyingly accurate at predicting experimental outcomes.
It is, but the mathematical machinery of QFT is highly abstract. It relies on a process called canonical quantization.
Okay, what is that?
Physicists take classical variables like position and momentum and replace them with mathematical abstractions called operator algebras. They calculate probabilities using non-physical mathematical spaces. TFH rejects this abstraction completely. It proposes to derive the entire menagerie of the standard model from purely physical first principles without ever using canonical quantization or operator algebras.
Which sounds like absolute heresy to a trained particle physicist.
Yeah.
How on earth do you create an electron or a quark without using quantum fields?
By relentlessly adhering to axiom 1, energy exists and nothing else does. There is only the single propagating scalar field, phi. In the standard model, physicists postulate a different fundamental field for every particle. There is an electron field, an up quark field, a down quark field, a photon field, a Higgs field. They are all stacked on top of each other. In TFH, there is only one field.
So what are particles then, if they aren't their own fields?
Particles are stable, highly localized, vortex-like configurations of that single scalar field.
Like whirlpools spinning within the moving 4D ocean.
Precisely. They're physically constrained geometric patterns. The math describes them as discrete Bessel-type eigenmodes confined at a universal equilibrium scale, which they denote as lambda e.
Okay, discrete Bessel-type eigenmodes is a lot of jargon. Let's translate that for the listeners.
Think of a guitar string. When you pluck it, it doesn't vibrate chaotically. Because it is pinned down at both ends, because its geometry is confined, it can only vibrate at certain specific, distinct frequencies or harmonics. Those distinct frequencies are eigenmodes.
So it can play an A or an E, but it can't play the mushy frequencies in between. It is quantized.
Exactly. The geometric confinement of the topographic wells naturally gives rise to discrete, quantized vibrations. In TFH, you do not need abstract mathematical operators to force the universe to be quantized. The physical geometry of the field vortices automatically restricts the energy into discrete, stable vibrational patterns. Those patterns are what we measure as particles.
And here's the claim in the sources that actually made me gasp. It's a massive, unprecedented flex. TFH claims to reproduce the full hierarchy of standard model fermions, meaning it accurately calculates the wildly different masses of the electron, the muon, the tau particle, the quarks, with percent-level accuracy, using absolutely no free Yukawa parameters.
To understand why that claim is so revolutionary, you have to understand a deeply frustrating flaw in the standard model. The standard model is incredibly accurate, but it is not entirely predictive. It requires dozens of arbitrary inputs. The masses of the fundamental particles are dictated by numbers called Yukawa couplings.
And where do the values for those Yukawa couplings come from? Do we calculate them?
No, we measure them in a particle accelerator, and then we manually type them into the equations. The standard model does not tell us why an electron has a mass of 0.511 mega electron volts. It just accepts the measurement and builds the math around it. It's like having a theory of architecture that requires you to manually measure every brick before you can explain why the building stands up.
So the standard model has all these dials that physicists have to tune by hand to make the math match reality. But TFH has no dials.
TFH derives the masses of the particles purely from the physical geometry of the field vortices. Because the eigenmodes are mathematically fixed by the topography, their energy levels, which translate directly to mass via E equals mc squared, are fixed.
That is mind-blowing. If they are right, it's like someone finally explaining the magic trick behind the entire universe. It changes physics from a descriptive science to a truly predictive science. But again, a beautiful derivation isn't proof. How do we prove that particles are actually just geometric whirlpools in a single wave?
We look for the absolute, make-or-break, falsifiable prediction of the entire TFH framework, the fundamental 2.05 GeV scalar mass gap.
The 2.05 giga-electron volt scalar, this is the smoking gun we've been looking for. Let's unpack exactly what this is.
If all particles are simply distinct vibrational modes of the scalar field confined at the equilibrium scale, then mathematically there must be a lowest possible non-zero vibrational state. It is the absolute baseline harmonic of the field itself. Think of it as the deepest, most fundamental tone the universe can ring at. TFH calculates the exact energy of this fundamental baseline mode to be 2.05 GeV.
And just to give some context for you listening, a giga-electron volt is a unit of energy used to measure particle mass. A proton is roughly 1 G, so this predicted particle is about twice as heavy as a standard proton. What would this 2.05 GeV particle look like to the physicists running the Large Hadron Collider at CERN?
The sources outline its signature with rigid specificity. It would be a scalar particle, meaning it has a spin of 0. It would be CP even. Crucially, it would be a standard model singlet.
Meaning it doesn't interact with the standard forces.
Correct. It does not carry an electric charge, so it doesn't interact with electromagnetism. It does not carry a color charge, so it ignores the strong nuclear force that binds atomic nuclei. It is almost entirely invisible to our normal detectors. It connects to the rest of the particle world primarily through an ultra-feeble connection to the Higgs boson, a mechanism they call a Higgs portal.
So it's essentially a heavy, invisible ghost particle that just sits there at the exact baseline of reality. And this isn't the only microscopic prediction TFH makes. The sources outline several other highly specific anomalies we should look for. They predict an essentially zero invisible decay width for the Higgs boson. They predict tiny topology-dependent shifts in the precision spectra of atoms and molecules. They even lock down an absolute mass scale for neutrinos, predicting them to come in at roughly 0.01 to 0.02 electron volts.
These are not vague philosophical guesses. These are highly specific, numerical targets that experimental physicists can aim their multi-billion-dollar machines at.
Let's speculate on the sociology of science for a minute here. The mainstream scientific community is notoriously conservative. But let's say experimentalists tune the detectors at the Large Hadron Collider. They filter through petabytes of collision data, and they actually find a previously unknown spin-zero scalar particle sitting exactly at 2.05 GeV, completely isolated from the standard forces. What happens to physics the next morning?
The fallout would be immediate and absolute. It would initiate a paradigm shift faster and more violent than any theoretical debate in the history of science. You would see Nobel Prizes awarded almost instantaneously. The textbooks on quantum field theory and general relativity would be moved to the history section. Funding priorities globally would shift overnight to map the scalar field.
It's that.
Because finding that exact particle wouldn't just be adding a new member to the particle zoo. It would be the definitive experimental confirmation that reality is built on a single damping 4D wavefront.
I have to represent the skeptical mainstream scientist here, though. I have to push back. We are talking about overthrowing frameworks that took thousands of the most brilliant minds on Earth a century to build. To look at the success of QFT and say, we are going to replace gauge bosons, quarks, the whole machinery with geometric modes of a single wave.
Right.
Well, doesn't that require an unbelievable leap of faith for the physics community? Why should they take this seriously today before the particle is actually found?
You are absolutely right to be skeptical. Physicists despise leaps of faith. They demand evidence, rigor, and testability. And the architects of the time force hypothesis understand this sociological reality perfectly. They didn't just publish a wild theory and ask the community to believe it. This brings us to why the TFH proposal is so uniquely compelling from a structural standpoint. In Volume D, they laid out a merciless open-source testing playbook. They provided the exact tools needed to either definitively prove the theory or violently and publicly kill it.
Let's get into the playbook for mainstream acceptance, the benchmarks and the falsifiability of TFH, because this is the wholesome X factor we talked about at the beginning.
The authors established a highly rigid, self-imposed benchmarking system to track their progress against the massive head start that mainstream theories have. They divide the maturation of their theory into 3 levels. Level 0 is the conceptual mechanism. Does the mathematical logic actually make sense without contradicting itself? Level 1 is semi-quantitative agreement. Does the theory produce numbers that are in the right ballpark, the right order of magnitude as observations? And level 2 is the ultimate goal, a precision fit where the theory matches the raw data as perfectly as general relativity or QFT does.
And what I found so incredibly refreshing reading these sources is the intellectual honesty. TFH openly admits that for many complex phenomena, they are currently stuck at level 0 or level 1. They are not claiming they have solved the entire universe today. They are outlining exactly what math still needs to be invented.
Yes, and they highlight specific cosmological arenas where achieving a level 2 precision fit would force the scientific community to abandon the standard model. The most prominent of these targets is resolving the Hubble tension.
The Hubble tension. For anyone who doesn't follow astrophysics closely, this is the biggest, most dramatic, unresolved fight in cosmology right now. We need to explain what the tension actually is.
It is a severe observational crisis. Cosmologists have 2 primary ways to measure the expansion rate of the universe, the Hubble constant. The first method looks at the very early universe, specifically the cosmic microwave background radiation left over from the Big Bang. They use satellites like Planck to measure the variations in this radiation, and the math spits out a specific expansion rate.
That's the early universe measurement. What is the second method?
The second method looks at the late modern universe. Astronomers look at relatively nearby galaxies, measure the brightness of exploding stars called supernovae, and calculate the expansion rate based on how fast those local galaxies are receding.
And the crisis is that the 2 methods give 2 totally different numbers. The late universe is expanding noticeably faster than the early universe measurement says it should be. Standard cosmology, with its fixed cosmological constant for dark energy, absolutely cannot reconcile these 2 numbers. They contradict each other.
Exactly. But TFH approaches the Hubble tension not as an error in measurement, but as a sharp consistency test for its core mechanism. Remember, in TFH, the expansion of the universe is driven by the universal damping rate, alpha 0. But as the wavefront propagates and the scalar field continually undergoes irreversible equilibration, the dynamics of the wave are not perfectly static. The expansion rate is dynamically evolving as the wave fatigues.
So TFH predicts that the expansion rate should be different depending on whether you are looking at the ancient past or the local present.
Precisely. The authors challenge the physics community with a mathematical gauntlet. If one specific constrained choice of TFH parameters, specifically the damping rate alpha 0 and the initial vibration spectra of the scalar field, can mathematically resolve the Hubble tension across all eras of time, the community will be forced to engage. It would prove that the tension is an artifact of trying to force a static cosmological constant onto a dynamically damping wave.
That is a massive prize to aim for. But the playbook doesn't stop with the Hubble tension. They outline several other strict observational windows where TFH predicts measurable deviations from Einstein's general relativity. The one that stood out to me the most was their prediction regarding gravitational waves.
Gravitational wave astronomy is a relatively new field. When unimaginably massive objects collide, like two black holes spiraling into each other, they send intense ripples through space. We detect these ripples using massive laser interferometers on Earth, like LIGO, and soon with space-based observatories like ELISA.
Standard Einsteinian physics says these waves travel infinitely outward, only fading because they're spreading over a larger area, like the ripples on our pond. But TFH predicts something extra.
Because TFH states that these gravitational ripples are propagating through a scalar field that is intrinsically subject to the universal damping rate, the waves themselves should experience an additional tiny bit of amplitude decay over vast cosmological distances.
An extra fading effect. The math models it as an exponential decay. Exp to the negative gamma GRU times distance over the speed of light.
It is a minuscule effect, practically unnoticeable for local black hole collisions. But for supermassive black hole mergers occurring billions of light years away, the new space telescope LISA should be sensitive enough to detect if the wave amplitude arrives slightly weaker than Einstein predicts.
They also predict that if you look closely enough, Newton's gravitational constant g might be weakly environment dependent. Because g is an emergent response of the topography, they suggest that in incredibly smooth, empty voids of the universe versus heavily scarred, dense galactic clusters, the fundamental strength of gravity might vary by a tiny fraction.
And they predict topographic lensing anomalies. They suggest we look closely at galaxy clusters where the bending of background starlight doesn't perfectly match the distribution of visible matter or the presumed halos of dark matter. Because in TFH, the light is being bent by the complex, history-dependent ruts in the scalar field, which don't always align perfectly with where the matter currently sits.
I want to focus on the sociology of this approach again because it is so rare. The true X factor of TFH isn't just the elegance of an energy-only universe. It is the utter vulnerability of the framework. The authors state explicitly in the text that the framework, quote, either succeeds as a tightly overconstrained model or fails decisively.
That phrasing is crucial. Tightly overconstrained means there are no free dials to spin. You cannot invent a new invisible particle, or tweak a Yukawa coupling, or add an extra curled-up dimension to make the math work if the observation doesn't fit. The math is locked in by the geometry of the field.
If the 2.05 GeV particle isn't there, the theory dies. If the gravitational waves don't show the extra exponential damping, the theory dies. They invite their own destruction.
That level of intellectual honesty is vital for a theory this radical. The authors maintain public refinement-needed logs in their papers. They openly publish the gaps in their knowledge. They list exactly where a fully worked-out perturbation theory is missing, where they desperately need advanced supercomputers to run numerical implementations on expanding wavefronts, and where the mathematical ties between the macroscopic gravity and microscopic quantum scales remain weak.
It is an open-source, intellectually wholesome way to propose a grand unified theory. We are so used to the trope of the lone genius declaring they have solved the secrets of the universe and everyone else is an idiot. But TFH is presented as a team building a rigorous scaffolding, admitting it's incomplete, and actively inviting the global physics community to come try and knock it down.
And that profound vulnerability is its greatest weapon against institutional skepticism.
But let's face the harsh reality. What if the physics community takes them up on the offer and they do knock it down? What if, 5 years from now, the LISA observatory runs the gravitational wave data and there is zero evidence of the extra amplitude damping? Or what if CERN does a dedicated sweep, analyzes every collision, and proves definitively there is no scalar particle in 2.05 JBO? Does the entire time force hypothesis just collapse?
Yes, and the authors accept that outcome completely. If the hard astronomical and particle observations do not match the rigid, derived predictions of the universal damping parameter and the geometric mass gap, the hypothesis fails. It will be discarded as a beautiful but incorrect idea. But taking that risk is the hallmark of true, rigorous science.
which is incredibly refreshing in an era of theoretical physics that sometimes feels lost in untestable mathematical abstraction.
Okay, we have covered an immense amount of ground today. Let's take a breath and recap the breathtaking scope of the deep dive we've just been on. We have looked at a proposal that seeks to cure the century-old crisis of time by reimagining reality from the ground up. It replaces the fragmented, broken lenses of modern physics with a single, energy-only, four-dimensional wavefront.
A universe where time is no longer a dimension you can move back and forth in, but simply the relentless forward progression of that energetic wave. A universe where gravity isn't a magical pulling force, but simply the geometric rut left behind by energy moving through the wave. Where the menagerie of subatomic particles are just spinning vortices confined in those microscopic ruts. And where the great mysteries of dark matter and dark energy are exposed not as invisible ghost particles, but just the natural stretching, warping, and fatiguing of the field as it propagates toward equilibrium. It is a stunningly cohesive and beautiful picture of reality.
It is mathematically elegant, philosophically economical, and most importantly, decisively testable.
But before we wrap up, I want to leave you, the listener, with one final mind-bending implication derived directly from the TFH sources. It's something we haven't touched on yet, and it deeply changes how we view the future of technology. The authors call it the universal decoherence floor.
This is perhaps the most profound philosophical and practical implication of living in a TFH universe. It has massive implications for the field of quantum computing. In standard quantum mechanics, to build a functional quantum computer, you have to perfectly isolate your quantum bits, your qubits, from the surrounding environment. You have to stop them from interacting with heat or stray radiation so they don't lose their delicate superposition. This loss of quantum state is called decoherence.
The underlying assumption in physics is that if human engineering could just build a perfect vacuum, perfectly shielded from the outside world and cooled down to absolute zero, a quantum state could theoretically last forever. You could isolate a secret from the universe permanently.
But the time force hypothesis dictates that such isolation is mathematically impossible. Because in TFH, decoherence isn't just an accident caused by clumsy environmental noise. Decoherence is intrinsically, mechanically tied to the cosmic damping rate, alpha zero.
The same mechanism expanding the universe is acting on the qubits.
Exactly. Because the entire observable universe is, at its core, a dynamically damping wave, there is an absolute, fundamental, irreducible limit to how isolated any quantum system can ever be. The sheer advancement of physical time itself, the radial progression of the wavefront, continually bleeds amplitude from every system. The wave forces the system to eventually damp out and decohere.
Let that sink in for a moment. No matter how advanced our technology becomes, no matter how perfectly we build a vault, no matter how cold or isolated we make it, the mere progression of time will break down the quantum state. The universe literally cannot keep a secret forever. The arrow of time will always find it, because we are made of time's movement.
It is a profound, inescapable reminder that every atom, every star, and every thought we have is ultimately bound to the propagation of the wavefront. We cannot isolate ourselves from the wave we are constructed from.
We started this deep dive talking about a broken X-ray machine. We realized that physics has been looking at reality through contradictory, fragmented lenses. TFH is proposing we throw out the X-ray machine entirely. It's offering us a radically new kind of scan, a dynamic MRI of the universe's energy field, showing us the living, moving, damping wavefront of reality.
We do not know yet if this new machine is calibrated correctly. The experimental data from CERN and space observatories in the coming years will be the ultimate judge of its validity. But the conceptual image it produces is undeniably compelling.
It really is. Thank you for joining us on this intensely complex and fascinating exploration of the time force hypothesis. Keep questioning the fundamental nature of time. Keep looking for the ruts in the topography, and we'll see you next time.